be 2 golden rules. I thought there could only be 1.
Oh, no, there's a whole bunch of golden rules. Okay,
Not be good.
so when you deal with velocity, velocity is probably the most specific unit that we'll cover in terms of vocabulary and how those words play out differently, like in a physics class, than in the world outside of the physics class. So, a couple of things. One of the things we'll talk about is known as frame of reference. So, frame of reference just refers to what are you analyzing, okay? So let me kind of give you the classic example. So right now, in the confines of this room, your velocity is 0, okay? You are not moving within the confines of this room, okay? And here's becomes the next part of this. So the frame of reference is just this room. Now, a lot of times within a frame of reference, you pick something known as the reference point. So the reference point is completely arbitrary, okay? But it determines how you're going to describe the motion. So here's the classic example. So here I've got the squirrel. If I drop the squirrel and I make my hand the reference point, you would say, oh, the squirrel is going away from the reference point. If I make my hand the reference point, then you say it's going towards the reference point. Both descriptions are equally valid. Okay, there's no right or wrong. So if I said, Louise, describe your position within this room. Someone walks in this room and doesn't know you and they want to find you. How would they find you in this room?
I'd say I'm at the middle area of where the desks are.
Okay? Give me that description relative to something specific, just not a general area, like a certain distance from something.
I'm probably like 2 yards away from Mr. Breakout.
Okay, so what you just did is that you established me as the reference point. Now, you say 2 yards away. Okay, let's go meters, okay, because we're in physics class.
2 meters.
Is that north, south, east, west, which direction?
I'd say, south.
Nope, you're north.
Yeah.
That's north. Okay,
That's north.
that's north.
Yeah.
That's south.
Because that way it's to the intermediate school.
That's west, yeah.
I'm not very
Gavin.
good.
South. Okay,
I'm not good with spatially aware.
okay, we're gonna get you spatially aware. So here's what Louise did. Louise used me as the reference point. He says, okay, Burkamp is the reference point. I am 2 meters north. Okay, cool, that's valid. He could have used the big red sign as the reference point, and he could have said, hey, I'm 2 meters south of the big red sign. He could have used the stapler. He could have used the fire extinguisher. There are any number of things he could have used as a reference point. It's completely arbitrary. Now, here's what's important, is that what you typically talk about is what's known as position. And that position is based upon your reference point, which is based upon your frame of reference. So we're talking about the frame of reference being this room. Louise picked me as his reference point. He goes, hey, I'm 2 meters away from that. And his initial position was 2 meters north. Okay? Now, here's what's important. Here's the room. Here's me. I can draw an arrow pointing towards Louise. Okay? And that's going to describe where he's at. So when you're talking about quantities in a physics class, you have 2 broad types of measurements. You have what we call scalar quantities, and you have vector quantities. So vector quantities only have magnitude, okay? So magnitude is just a fancy way of saying, hey, it's a number. So here's the classic example. Louise, I said, Louise, where are you from me? If he says, hey, I'm 2 meters away, that's just a magnitude. So if Louise is 2 meters away from me and that's all he tells me, I don't know where he is. I don't know if he's up in the ceiling. I don't know if he's dug a hole and he's down in the basement. I don't know if it's north, south, east, west. Okay? It's just a number. Now, there are certain quantities that are cool. That's all we need is a number. So mass is an example of a scalar quantity. What's the mass? It's 1 kilogram. It doesn't make any sense to say, oh, that's 1 kilogram north, or 1 kilogram negative, or 1 kilogram positive. It's just a number, okay? Speed, okay? Speed is also a scalar quantity. If I said, Dylan, how fast, roughly, what was your average speed when you were driving to school this morning? Average.
40.
40, okay? 45, okay? So if Dylan just says, I said, hey, what's your average speed? 45 miles an hour. Now, I don't know which direction he was traveling. I don't know if it was north, south, east, west, up, down, in a helicopter. I don't know, okay? Maybe he was underground, boring straight up through the school. I don't know. But if all he says is that his average speed is 45 miles per hour, that's a scalar quantity. So your car has a speedometer, because it just tells you how fast you're going. Okay? That's it. It's a speedometer. That's it. So don't look at scalar quantities and go, oh, they're just not as cool because they only have magnitude. They're just not as important. No, there are some very, very important scalar quantities in physics. They're just limited to having magnitude because it doesn't make any sense to give them a direction. Mass, vitally important. It just doesn't make sense to give it a direction. Energy, vitally important. Doesn't make sense to give it a direction, okay? But velocity, acceleration, force, momentum, there are a bunch of quantities that do make sense to give it that. Now, a vector quantity has two things. It has magnitude and it has a direction. Now, so as soon as Louise says, I'm 2 meters north, that now becomes a vector quantity because he tells me the value and he tells me the direction. Dylan, you said on average you drive 45 miles per hour to school. Do you drive north, south, east, west? On average.
West.
West, okay?
No, north. No, south. South.
South?
Whoa.
South.
Okay.
Yeah.
You're going this way. From the
Yes.
north to the south.
Mostly this way.
Okay. So now, as soon as Dylan says, hey, I drive on average 45 miles per hour south, now that becomes a vector quantity because he's given me magnitude and he's given me direction. Now I not only do I know how fast he's going, I know which direction that he's going. So, this is the bigger idea. Within this frame of reference, Louise's position is not changing, okay? He is staying there at 2 meters north of me, because I'm his reference point. Now, Louise gets up and he walks to the back of the room. Louise moves back here. And Louise ends up 6 meters away, okay? Now his position has changed. Now we have what we call a displacement. Okay, and this is why I said you have to pay attention to the vocabulary. Displacement is a vector quantity. Because what I can do is I can draw a vector and go, Louise went this direction. He went 4 meters north. Now, if Louise just says, hey, Louise, did you move? He goes, yeah. Where'd you move? I moved 4 meters. Now, if Louise just tells me he moves 4 meters, cool. I'm happy for Louise. Good for him. I don't know which direction that he went. I don't know if he climbed a ladder. I don't know if he fell down a hole. I don't know if he went left, north, south, got shot out of a cannon at a 45-degree angle. I don't know. Okay? All I know is that he moved 4 meters. So if you just talk about how far you go, that's distance. That's the scalar quantity. So Dylan, go back to you. Roughly, how far away from the school do you live? Roughly.
5 miles.
Okay. Now, if Dylan just says he lives 5 miles away from the school, cool. I don't know which direction that he lives. I just know that he lives 5 miles away. That's a scalar quantity. Now, Dylan says, I live 5 miles north of the school. That then becomes a vector quantity, because now he tells me how far and in which direction he's moving. So, when you talk about displacement, there's a whole bunch of different ways you can calculate displacement. The simplest is P minus P naught, which is position final minus position initial. So if Louise's final position is 6 meters and his initial position was 2 meters, he would have a displacement of 4 meters. Okay? Again, that, in this case, this is a positive value. He went in a particular direction. Cool. Now, if I said, Louise, what distance did you travel? He would just say 4 meters. Because that's just how far he went. So the beauty of this, when you see that what implied within this, is that's a positive 4. Okay, cool. Louise went in a particular direction that we defined as positive, which is completely arbitrary. If Louise wanted to, I said, Louise, where are you at? Louise could have easily have said, Mr. Burkham, I'm at negative 2 meters. Okay? He could have said I'm at negative 2 meters, which would have been cool. There's nothing magic that says, oh, this particular value is positive, this particular value has to be negative. What you define as positive and negative is completely arbitrary. Now, if Louise gets up and moves to a value of negative 6 meters, which is cool, that's completely valid. He could have gone from negative 2 to negative 6. We would have done the exact same thing. Our final position was going to be negative 6 meters minus an initial position of negative 2 meters. Now, I take negative 6 minus negative 2, what do you get?
-4.
I get negative 4. Now, there are certain things I want you to begin to get out of your minds right now. That positive displacement or positive velocity means that you're going forward. And negative velocity and negative displacement means that you're going backwards. Horrible. No, get that out of your minds right now. Okay? Out of your minds. What you define as positive and negative is completely arbitrary. If I take the squirrel and I define down as being negative, hey, he's going to have a negative velocity. If I define down as positive, he's going to have a positive velocity. Okay? So there are certain things I have to begin to exercise from these preconceived notions that you have. One is that positive means you're going forward, and the other is that negative means you're going backwards. It can happen. Okay? It can happen. But that isn't an absolute, always set in stone truth. Okay? All right. So, let's talk about velocity. There's a whole bunch of different ways you can calculate velocity. One is that it's change in position over time. Now, notice I did not say change in distance. Okay? I said change in position. So, if Luis, do you want to do positive or negative first?
Negative.
Okay. So, if Louise ends up at negative 6 meters minus negative 2 meters, and let's say that that took 2 seconds for him to go from here going backwards. That's going to be, according to Gavin, negative 4 divided by 2 seconds, which is going to be negative 2 meters per second. Okay? Now, here's another common misconception people have. They want to associate positive velocity with moving away from the reference point and negative velocity moving towards the reference point. Get that out of your minds right now. Okay? I'm the reference point. Louise was going away from the reference point. He has a negative velocity. Okay? So again, get out of this preconceived idea that negative velocity means you're going away from the reference point, positive. No, stop. All this means is that it's a direction. So what I could do is that I could draw an arrow and going, that arrow could represent a couple of things. It could represent his displacement. It could also represent his velocity. Okay, cool. Now, let's say Louise says, no, Bergkamp, it's Monday, I'm excited about learning. I want that to be positive, okay? So then he could go, okay, he's going to end up at 6 meters, minus 2 meters, we get 2 seconds. The only difference is that that becomes positive 2 meters per second, okay? And again, in both situations, he's traveling from here to the back of the room. In both situations, he's moving the same distance. The distance would be 4 meters. But in one situation, the displacement is positive 4. In another situation, the displacement is negative 4. In one situation, the speed or the velocity is positive 2. The other one, the velocity is negative 2. Now, speed, though, is a scalar quantity. Louise went 2 meters per second. Now, if that's all you tell me, hey, how fast was Louise moving? 2 meters per second. Cool. I don't know which direction he's going. I just know that he's moving 2 meters per second. But if you say, hey, within this frame of reference, with Bergkamp as the reference point, you go from negative 2 to negative 6. You go from positive 2 to positive 6. Both situations are equally valid. Whether Louise wants to go from negative to negative, positive to positive, doesn't make any difference. Okay? Does not make any difference. So, one way you can visualize this, oddly enough, is kind of a visual with a banjo. Okay? So, that's okay. So, if something's vector quantity, you can represent it with a banjo. Okay? It's true. So, if you consider this banjo being a vector quantity that represents velocity. So if I'm the reference point, and this banjo is pointing in that direction, Louise is going away from the reference point. It might be positive, it might be negative, I don't know. All I know is that he's going in that direction. Now, here's going to be something that's important. Louise is going to get to the back of the room, and he's going to turn around and he's going to come back this way. Okay, Louise is going to change direction. Okay, Louise is going to change direction. Louise, do you want to do with positive or negative first?
Positive.
Okay, now we switch to positive. Okay, so here's what happened. We're going to represent this a couple of different ways. We're going to look at this on a position time graph. Okay? Louise started at 2 meters, because you want to deal with positive first, right? And he ends up at 6 meters. And I'm going to draw this line like this. So that took 2 seconds. Okay? So, now we have a position time graph. So what we're showing is that Louise started at 2 meters. He's going to end up at 6 meters. And that's going to take 2 seconds. Now, Dylan, you're going from 6 to 2, right? That's your displacement, 6 to 2. And this time is 2 seconds. Do you have enough information to calculate the slope of that line?
Yes.
What would the slope of the line be?
Up 2/1.
Yeah,
2/1.
2 meters per second, right? Okay, slope of the line. Now, what does the slope of the line represent on a position time graph? Velocity. Because it's meters per second.
Oh my God.
Woo! How cool is this? So, on a position time graph, slope represents velocity. Okay? Cool, right? Now, it's a straight sloping line. When you have a straight sloping line on a position time graph, this is a very specific type of velocity, which we call constant velocity. So when you have constant velocity, that's shown by a straight sloping line on a position time graph. And this is a logic problem. Slope of a position time graph gives you velocity. So if the slope is constant, guess what? The velocity is constant. He's not speeding up, he's not slowing down, he's moving. Pointed in that direction. Now, Luis gets to the back of the room. He goes, man, that's a long way from everybody. You know, I left my headphones up there on the table. I gotta go back and get my headphones, okay? Now, this is vitally important. Luis is gonna start at 6 meters and he's gonna come back down to 2 meters, okay? Listen to me very carefully. He's starting at 6 meters and he's gonna come back to 2 meters. So Luis, this is your story, right? On the way back, what's your initial position? 6 meters or 2 meters?
6.
So his initial position is going to be 6 meters. His final position is going to be 2 meters. Now, to calculate your displacement, it's always final minus initial. So I'm going to take final position of 2 meters minus 6 meters, and let's say that 2 seconds, it took 2 seconds, and oddly enough, we're going to get negative 2 meters per second. Okay? Now, Luis, did your direction change?
Yes.
What?
Because you went away from the reference point and then you came back towards the reference point. His direction changed. What do you notice about the sign of the velocity? It changed as well. It went from positive to negative. Okay? So in this situation, we're going to draw this line like so. Okay? Now, the slope of this line is going to be negative 2 meters per second. So here's one of the most important rules to remember. Anytime an object changes direction, the velocity changes sign. Okay? There's no exceptions to that. Now, we're not going to be dealing with circles for now. The only thing we're going to be dealing with is motion like on a number line in one particular axis. So basically what happened is that Luis had his banjo pointing in that direction. He gets to the end, he turns around, boom, banjo points back in the opposite direction. So anytime the banjo flips direction, that means that the object is going to change direction, which means the velocity has to change sign. There is no exceptions to that whatsoever. Zero, zip, none. So I take the squirrel. I throw the squirrel up in the air. Vanessa, did the squirrel change direction? Yes. So what had to happen to the velocity? It had to do what?
Switch.
Yeah. Positive to negative, negative to positive, however you want to define the system. Okay? So what that means is that you can take some very, very, very complex situations and break it down into a central idea. Okay, hey, I throw that thing up in the air. Velocity changed direction, and the velocity had to change sign. Okay? No exceptions whatsoever. Now, here's one of the things I want you to begin to get out of your mind right now. You go, oh, positive velocity means that you're going away from the reference point. Negative velocity means that you're coming back towards the reference point. Have an exorcism. Get that out of your mind right now. Okay? Stop. Because here's the reason why. Now, Louise, we're going to deal with the negative side of this problem. So typically, you define the reference point as being 0. You don't have to, but that's almost how it plays out. So implied within this is that I'm the reference point, and I'm defined as 0. Okay? It doesn't have to be. I could define my position as 2. Louise would have been 4. The final position out there would have been 8. Okay? The reference point does not have to be 0. But a lot of times, most of the time it is, because it just makes the math work out a little bit simpler. Now, here's what we could have done. Louise could have gone from negative 2 meters to negative 6 meters in 2 seconds. So his position time graph, come on, why don't you do that? Would be like this. Okay? So, here's where you cannot get lazy, okay? You cannot get lazy in terms of position final minus position initial. So in this situation, my final position is gonna be -6 meters minus -2 meters, okay? Don't look at this and go, oh, -6 and -2, my displacement's gonna be -4, okay? You have to pay attention to the mathematical side of what's taking place. Because if you don't, you're going to get numbers that don't make any sense. So, here's the story. I got -6 minus -2, I get what? -4. Divided by 2 seconds, I'm going to get -2 meters per second.
So, that's hard.
So, here's why this is important. If you had just said, oh, he goes from 6 to 2, that would be +4. Divide that by 2 seconds, you get 2 meters per second. So this is why you have to be consistent. Because on a velocity, on any graph, remember anything that has a positive slope is going up like this. Anything that has a negative slope, no matter where you are relative to 0, is a negative slope. If you don't pay attention to that subtraction, and you said that's +2 meters per second, that doesn't fit with the sign of the slope of the line. So if you did that and go, oh, that's +2 meters per second, +2 meters per second would make that line go up like this. That's not what it's doing, okay? That line's coming down like this. Now, Louise is now going to turn around and he's going to come back. Again, pay attention to the signs. Now, I've got -2 meters minus -6 meters over 2 seconds. And that's going to be +2 meters per second. Oh, now that slope matches a positive value because that's going to be a positive value. Notice that matches that positive value, no matter where you are relative to 0. Velocity calculations aren't inherently difficult. Where they get difficult is if you try and shortcut what you're subtracting. That's where things go south. Now, notice that Louise changed direction. He went from -2 to +2. His velocity changed sign. He changed direction. Got it? Good. Okay, Louise, stop that. Stand up.